Morning, everyone. So over the last 2 days, we've been looking at reactions of organic chemistry. We started out looking at alkanes, which were very low in reactivity, only went through combustion and under presence of really high energy sources. We then switched over to alkenes. Alkenes, because it's a very electron-dense region, we saw that we can actually add electrophiles across this double bond. A double bond becomes a single bond. And then yesterday we worked our way towards alcohols. Alcohols sort of represent the most reduced form your compound can actually be. In the presence of oxidizing agents like potassium permanganate and dichromate, we can actually oxidize it depending on the primary, secondary, or tertiary. That actually controlled what products were possible. For all this here, I would encourage you every day, just see if you can sketch out this mind map for yourself. I know it is increasingly getting larger and larger. We're even going to add to it in today's lesson as well. But the more times you sort of sketch down this mind map here, it'll help you just sort of keep the reacting conditions clear. I'd encourage you, as you draw this mind map, draw it the same way every time, so you have a little bit of consistency here, but at least you do want to know how to interconvert from one family to the other. In a later section, we're going to look at, it's going to be called retroactive synthesis. And basically what it is I'm going to have some target molecule, and you're going to find a way that actually gets you to that molecule. So more on that later on. Let's start off here with our alkanes. That was our very first family that we looked at here. Alkanes are a nice beginning place because they're really low reactivity. A lot of things that end up doing combustion, so I'm just going to leave a CP, combustion products here over here. And I know that it requires oxygen. I can assume complete combustion unless otherwise specified. Alkanes have really strong single bonds, so only in the presence of UV light here, we manage to do a substitution reaction through a free radical mechanism. You do need to know that mechanism. So if I end up reacting it with, let's say, Cl2 or Br2, we can end up substituting some of the chlorines and bromines onto the alkane. And this one here ended up forming a halogenoalkane. It's an alkane with a halogen on it, or you can call it an alkyl halide. Both names are perfectly fine. Today we'll actually do extensions from this. What are some reactions that alkyl halides do? It's going to make this mind map even bigger. The second day we did was alkenes. Let's make sure we know how to interconvert alkenes back to alkanes. That was a process called hydrogenation. So the chemical we needed was hydrogen. This one needed a little bit of reacting conditions. It needed nickel as a catalyst. It needed slightly hotter than room temperature. Let's just quote 150 degrees. What are some other things that we had added to alkenes? Basically, it's electrophilic addition. I'm adding an electrophile across a double bond. I can add an HX. This one here just occurs at room temperature. That's a nice test for whether it's an alkane or alkene. If it already adds without the presence of UV light, it's probably the indication of a double bond is present. So that happens at room temperature. Forming a halogenoalkane, we can form a dihalogenalkane if I end up just adding the halogen directly. So dihalogenation or dihalogenoalkane, sorry. So we end up adding an X2, right? F2, Cl2, Br2. They will differ in terms of which one is easier to substitute on and not. To get a little bit more on that in today's lesson. We did see alkenes could add to themselves multiple times. So let's just add one bubble here. They can end up forming polymers when an alkene just adds to other alkenes. Right? They end up forming long chains. They just repeat n times. The most important one, however, was an alkene. It's a reversible reaction here. In the presence of concentrated sulfuric acid, that one there is a catalyst. It can add water across the double bond. We end up forming an alcohol family. And that's what we learned last day. Alcohols are sort of the most reduced form. We saw what it meant to actually oxidize. Alcohols can also burn. So in the presence of oxygen, combustion product, alkenes can burn as well. Typically a little bit more partial combustion, a more dirty flame there. But then what we learned yesterday was depending on the degree of alcohol that we had, we can actually get different products. So let's just go down here. Most of them are going to involve using acidified dichromate. Acidified dichromate here is one example of oxidizing agent. Sometimes they just say plus O, sometimes they use potassium permanganate, no problem. But this sort of the outcome is going to depend on whether it's first degree, second degree, or third degree. So primary, secondary, and tertiary. The easy one is tertiary because a carbon is bonded to 3 other carbon neighbors. So if I have a tertiary carbocation like this, I do want to oxidize it. I do want to get more oxygens. I want to lose hydrogens. But that would actually involve me breaking apart the parent structure pretty much doesn't break, so this one here will be no reaction. So tertiary carbocations you can't oxidize. A secondary carbocation here, so if it had an H instead, sure, I can break a CH bond, and I can end up forming, this one here ends up forming a C-double-bond-O. That was called a ketone. Some other sort of added notes we can add here is we can say this one here requires a heat treatment. This one here you can say reflux or distillation, doesn't really matter. You basically heat it, that's the only product possible. We have a C-double-bond-O somewhere mid-chain. The primary alcohols were the most interesting here. Primary alcohols here only have one carbon. If not, they have all hydrogens neighbor. That could still be fully oxidized. I can break CH, no problem. This one here can end up forming two families. They can end up forming an aldehyde family. For the aldehyde, we want to heat and we want to do a distillation. Aldehydes have no hydrogen bonding, so they boil first and then they can be tapered off into a collecting flask. Or if I run it through heat and I just reflux it, I just heat it up until it's completely done, it's going to end up forming a carboxylic acid. Okay? So now we're seeing sort of ways to interconverting sort of one family to the other family. I'll give you a quick example of an alcohol reaction just so that we're on the same page. And then today we're going to look mainly at alkyl halides and what are some reactions that branch off from there. Okay? So let me just give you an example of a alcohol family. So let's do a cyclopentane. It happens to have an OH here. I'm going to put it under acidified dichromate. I can write out the whole thing. I can say triangle means heat. Heat under distillation or reflux, doesn't really matter. All you need to say is this primary, secondary, tertiary? So the carbon that is involved with the functional group, this carbon happens to have two other neighbors. This is a secondary carbon. So yes, I can oxidize. It's not no reaction like tertiary, but when it oxidizes, it only ends up forming. We still have our carbon ring. Our parent is pretty much still intact, but we end up oxidizing and we end up getting a C-double-bond-O. This is called a carbonyl group. It's happening mid-chain. We end up forming a ketone family. Right? Let's take, I'm going to draw it, propanol. Okay, 1-propanol. Okay. What if I put it under, sometimes I just say plus O, right, as a generic oxidizing agent, KMNO4, under heat treatment, and I'm going to do a reflux. All you need to say is, okay, what degree alcohol are we? This one here, the carbon involved with the double bond, it's holding a bunch of hydrogens. It only has one carbon neighbor, so this is a primary carbocation. Under reflux, I basically heat it until the reaction is completely done. This one will be fully oxidized to form not only C, sort of single bond OH, this is going to end up forming a carboxyl group. It has now gained an extra C-double-bond-O, and now we have the rest of the molecule. So you notice it has broken off a CH. Part of the structure has to break off so that I can gain more bonds to oxygen. Earlier I was just bonded to one oxygen, now I'm bonded to two oxygens, and it's even a double bond to an oxygen there, but that's now a carboxylic acid. And you should be able to name these ones and all that. Okay, so that's where our mind map actually helps us identify is depending on what family you are, depending on what the reacting conditions are, they just give you this sort of middle ground. They can just ask you what's the product, or they give you the product and they ask you, well, what are the conditions that we need for this to happen? Okay. Today, as I mentioned, we're going to look over at the alkyl halide family. Again, let's just place ourselves here. We did alcohols previously. We're now focusing on alkyl halides or halogen alkanes. These are already substituted alkanes. We're going to find that it's actually that substitution portion of it that actually allows it to actually react. So alkyl halides, we're going to run into something called an Sn1 and an Sn2 type mechanism. So we'll see that. It's actually the polarity of the carbon-halogen bond, where the halogen is Cl, Br, and I. F is not included because sometimes F is so electronegative, ends up being almost like ionic. So we just deal with these lower activity halogens. So it's actually the polarity of this carbon halogen bond that actually makes it reactive. So let's imagine I have CH3 and then I have a chlorine group. Okay. Normally I'd say, well, you're an alkane. Your bonds are really strong here. You're not very reactive. But now that you're actually a substitute alkane here, the carbon and chlorine or carbon with whatever X is always a polar bond. The carbon is always a slight positive. The chlorine is always a slight negative here. It's actually that polarity that actually makes me susceptible to attack. What am I going to be attacked by? because the carbon has a relatively positive region, I'm going to find something that is a nucleophile. A nucleophile, sometimes they just put N for it, but a nucleophile is already very electron rich. The electron rich, it is always going to be negative attacks positive. This nucleophile is going to try to attack the positive end and kick off the halogen. So this is why it's going to eventually be referred to as nucleophilic substitution. A nucleophile comes in and tries to put its place for where that chlorine is. Okay. So let's look in little details here. The carbon carries a partial positive charge. It's susceptible to attack. It's sort of a positive end here. It's vulnerable for nucleophiles to actually come in. The alkyl halide is referred to as the electrophile. This one here is the electron deficient region, right? Because it doesn't have a lot of electron density. It wants negative things to come and attack it because it likes electrons. It is filio to electrons. It likes electrons being currently electron deficient. It doesn't have electron density. Whereas my attacking group this time here is the nucleophile. Right? The nucleophile, because it likes nuclei. Well, nuclei here is positive. The only reason why I would like nuclei is if I am electron rich, if I have a lot of electron density here. At the end of the day, I remember being really confused. What do you mean electrophile, nucleophile? It is always going to be negative attacks positive, but we're just looking, sort of taking a step back, and we're saying, well, what's ended up happening? In this reaction, as we're going to see, a nucleophile is the first thing that comes in and attacks. Overall, if the reaction occurs, the nucleophile substitutes itself onto the electrophile, so we're going to call it nucleophilic substitution. That's the overall reaction that occurs. This type of reaction is called nucleophilic substitution because the halogen, the chlorine or the bromine or whatever attached in the end here, is actually being replaced by the attacking species here. So let's just do in general here. We can have a nucleophile like OH minus. You're never going to have a bottle of just pure OH minus. Maybe that actually came from NaOH. Again, NaOH guarantees me it's a soluble salt. It becomes Na plus and OH minus. It ends up providing the hydroxide ions I need. Hydroxide is very electron rich. It has a lot of electron density here. When it tries to attack this alkyl halide, it's going to attack the positive part, right? There's a polarity here on this carbon halide bond here. It's going to attack the partial positive side here and ending up removing the halogen. So therefore, we end up having the OH that's substituted for the R, and the X gets kicked off, where the X is chlorine, bromine, or iodine. So let's just do an example of this one here. So we'll take CH3, CH2, Br in the presence of OH minus. Okay. First thing you need to recognize is this one here is an alkyl halide. The carbon that is currently attached to the bromine, there's a certain polarity there. The OH minus is a nucleophile. It's very electron rich. The nucleophile is going to attack the positive side of the carbon. This bond here is going to end up releasing off the bromide, and therefore we're going to have CH3, CH2 now attached to an OH instead, and poor old bromide gets kicked off. Bromide actually takes on a negative charge here. That bond there, both of the electrons went to bromide, so therefore it's negative overall. We have one neutral, one negative, one neutral, one negative. The charges are cancelled. Okay. Now, here's the confusing thing. This reaction, this substitution, actually could take place via two different mechanisms. One's called Sn2, we're going to do first, and Sn1. In tomorrow's lesson, we're going to come back and we're going to talk about, well, which one is it more likely to be? And today, I just wanted to introduce this mechanism to you. You need to know what Sn2 stands for. Sn2 stands for substitution. We talked about something switching places, right? So two things becomes two things. It's nucleophilic. It's the nucleophile that's attacking. It's the currently electron-rich thing that's attacking. That's where the nucleophilic part comes from. The 2 is actually confusing. The 2 actually refers to the molecularity of the reaction. The molecularity, if you remember back in our reaction kinetics here, bimolecular means a rate order of 2. So it's second order overall. So it's like having a rate law here. Rate is equal to K. We're going to see what the constitutions depend on, but it's like being second order overall. Okay, so that 2 actually stands for the molecularity. We're actually going to see this takes place in one step. Right? They can't have gotten any more confusing. Later on, when we do an Sn1 mechanism, you might think, oh, one step. Well, no, Sn1 actually takes place in 2 steps. The 1 or the 2 refers to the rate order. It refers to the power in my rate law. Okay? So let's just have a look here. First thing you'll note is Sn2 and Sn1 are going to have it's a really common reaction. It's just whether it takes place all in one concerted step or in two different steps. So let's take a look at how the substitution can happen via the Sn2 mechanism. So let's recall that we learned about single electron pushing arrows. This one here was called a fishhook, right? Because it is just a half arrow. Where did we see that one there? Let's say I have a chlorine. For alkane reactions, we had a homolytic fission. I had one electron go back to each neighbor. I have a chlorine radical and chlorine radical. That was just one electron going to each side. For even our alkene mechanisms and alcohol mechanisms, we've been doing double-headed arrow. The double-headed arrow, this is actually not our first look, but our double-headed arrow just refers to both electrons are actually much more common, okay? And it's actually both electrons, so charges will actually change, okay? So here's what I want you to focus on. So this is currently my alkyl halide. I had my hydroxyl group as the nucleophile. This one here is going to be the one that attacks. It's the polar bond that actually makes it susceptible. Because the electronegative halogen here is going to be kind of negative, the carbon is kind of positive, the nucleophile is going to try to attack the carbon and try to attack, switch places with the X group. It is going to depend on what these R groups are. R groups usually refer to the rest of the chain. That actually is going to decide later on whether it's SN1 or SN2. But so far in the SN2 mechanism, all of it occurs in one step. We say it's a concerted step. It just happens all at once. So as a transition state, this happens as a sort of middle state here. At first, I had carbon. It had 3 R groups. The geometry is going to be important here. It had an X group. And basically, my OH is now forming a new bond trying to attach to the carbon here. Okay. The terminology here, they say we have a 5 coordinate. I have 5 things currently present, but this one here is a transition state. This one here is at the top of my activation barrier. You cannot collect this, so that's why they say this is one concerted reaction. It happens all at once. Okay, so if I were to draw an activation barrier profile for this one here, I don't necessarily know endo or exo for this, but the transition state here is occurring at the activated complex. It's not something that you can actually collect. It's really high energy. It's just in the process of breaking and forming bonds. Well, what bonds are breaking or forming? I'm trying to create a new bond with the O, so this bond is just starting to form, as the C to X bond, which was naturally there, this bond here is just starting to break. So it's all happening in one step, even though I call it an Sn2 mechanism. And what ends up happening, if the reaction occurs, if OH is a stronger nucleophile than the X, if it ends up bonding better, the OH actually attaches to the carbon. And looking at sort of the umbrella here, looking at the orientation, you actually can see, like an umbrella, we'll start off with an umbrella, maybe like an upside down umbrella like this. So that's when on a really windy day, your umbrella is sort of flipped backwards. You'll notice because the OH is attacking from the underside of the umbrella, now the umbrella is actually the correct orientation. They actually switch this up on you, so it's a little bit harder to see. But overall, we are going to get an inversion of stereochemistry. If this one here were an S isomer, this one here would be an R isomer. We would actually have flipped orientation. So we call that stereo inversion. The stereoisomers, the R, S that we talked about, has now become a mirror image. It's like going from an umbrella one way to an umbrella flipped the opposite way. So what are some key features to this SN2 reaction? The substitution occurs in one step. The 2 does not refer to how many steps. The 2 actually refers, like I mentioned, to the order of reaction. The 2 stands for bimolecular. This attack, because it all occurs in one, if I actually talk about a rate law here, the rate is going to be proportional through some rate constant. That depends on temperature. It's going to depend on the concentration of both things. It depends on the concentration of my alkyl halide. How much alkyl halide do I have present to the power 1? And because the nucleophile is attacking in this step, it's part of the rate determining step, it also is present. And this one here is also a rate order of 1. If I add 1 plus 1, you notice we're actually second order overall. Okay? And the SN2 refers to that second order. That's referred to as the molecularity. I want to review that term with you here. Molecularity is how many atoms am I trying to collide? Well, they all had to collide all at once. The halide and the nucleophile had to be present. The reaction passes through a 5 coordinate transition state. 5 things are there. That's the activated complex. That's the really high energy state here. It's just starting to rearrange bonds. You cannot collect and isolate a sample of this one here. Okay. So as the new bond between the nucleophile is forming with the carbon, the halogen, we're going to call it a leaving group because that one there is now on its way out. It's actually trying to escape. That's the thing that's actually being replaced. Okay. But the key feature I want to just emphasize here, again, is that 2. The rate actually depends on both reactants. So you can change the concentration of the hydroxide or the alkyl halide, and both of them will have dramatic changes in terms of the speed of reaction. Okay. As we start, we're going to look in more detail with Sn2, but as we start switching over to Sn1, there's going to be a lot of things that are similar. It's still going to be the polarity that's susceptible to attack. It's still going to be the nucleophile that actually attacks, but it's just through a mechanism that actually takes place in 2 steps. Okay. So let's just practice a question before we go through here. We have 1-bromobutane. It reacts with potassium hydroxide, and we're told it does via an Sn2 mechanism. Let's see if we can label who's nucleophile, electrophile, and whatnot, and then draw out the product with the mechanism. So what I'm going to start off with here is just bromobutane. So I have butane, so I have 4 carbons in a row. I have 1 bromo, so that means the bromine is on there. That's where my halide part is attached to. This is going to react with potassium hydroxide. I don't really care about the potassium part. It's just the hydroxide that I actually care about. It's the hydroxide that's the really good nucleophile. Okay. So what I usually do here is I usually try to show the stereochemistry inversion. I usually focus just on the carbon that's involved with the functionality. It's this polar bond that's going to be susceptible to attack, not the rest of this molecule. So let me see if I can just sketch it out for you. I'll try to do that umbrella analogy a little bit better for you. So far, let's say I have carbon, we have a bromine. This carbon is holding on to 2 other hydrogen neighbors. So I'm going to say maybe a hydrogen back and a hydrogen forwards. It's holding the rest of this chain here. I'm just going to condense that part there. That just comes along for the ride, C3H7. Okay, so that's exactly the same 1-bromobutane. What we do now is we're going to take our hydroxyl group here. It's the O part that actually has the electron density. The formal charges are the negative is around the oxygen. The O part is going to attack the relatively positive side of the polar bond. It is a double-headed arrow because both electrons are going to data bond. What's going to happen here is all in one step, I'm going to give you the transition state because they asked you for showing the representation for a transition state here. We're going to go through a situation where the carbon still holds its bromine, still holds the 2 hydrogens, and just in the process, we now have the OH beginning to attack the carbon, and this other bond here that's going to release this propyl group here is just starting to break. But all of it occurs in one step. So this is a transition state. This is sort of midway through your reaction. This is not an intermediate. We're going to keep going here. If the reaction occurs, I'm going to then have an OH. I have my carbon. My bromine is going to now be bent on the top here. I'm going to still have my hydrogen to the back and the hydrogen to the front here. Using my umbrella analogy here. Here was my umbrella that was sort of the upside down umbrella, a really windy day, because the nucleophile has actually pushed it through. What's actually the geometry here? This one, if I have carbon with actually 5 domains, you should be able to tell me this part here is actually trigonal bipyramidal, right? So it's actually flat in the middle. As that happens, because the OH is pushing in on one side and the other side is actually leaving at the same time, it ends up flipping the planar part and it actually converts my umbrella to actually flip the opposite way. It flipped this way first, and now it's flipping the other way. So if this one here were R or S, I know I have 2 similar groups, so there's no optical isomerism, but if this were R, it would be S, or if this S, now it's flipped to R. There is a stereochemistry inversion there. Okay. Let's see if we can identify the bits here. The nucleophile is the thing that's attacking, the thing that's going for the positive part. So the OH here is the nucleophile. The electrophile is this entire alkyl halide part, so electrophile. The leaving group, as the name suggests here, is the chemical that leaves. Well, the thing that got lost is C3H7. Now C3H7 with a negative charge here. This one here is my leaving group. Now, typically we'd be in solution. We're going to talk about some solvent effects in tomorrow's lesson as well. This reaction is going to depend on a couple of things. It depends on, does the nucleophile make a stronger bond or the leaving group make a stronger bond here? The other thing that's not immediately obvious, again more on this tomorrow, is depending on what are the substituents, depending on whether this is a primary carbocation or secondary or tertiary here, there's actually some sort of bulky groups here, some sort of larger groups. Hydrogens are nice and tiny. It might actually interfere with hydroxide actually coming into attack. So more on that in tomorrow's lesson. Let's just continue onwards with the next page here. Hydroxide is not the only nucleophile. Ammonia can actually attack this halide via either mechanism. I haven't showed you the Sn2 mechanism just yet, but totally possible here. And that can yield a primary amine product. So let's take ammonia. Ammonia is my neutral molecule here. Ammonia, it could even be an amine. Amine here is a strong base, but here they're actually just looking at ammonia. I'm just going to write it NH3 like this. So therefore you can see, well, ammonia has some electron pair that I can donate. That actually makes it a Lewis base, if you remember from our acid-base chapter. Again, I'm going to attack the carbon side, the partial positive side, either in one concerted step or not a concerted step. I notice that the umbrella is flipped around. I used to be flipped one way and now the other way here. I go through this transition state. So I go through a process where my carbon with the R groups, R just means the rest of the molecule. My R groups are still temporarily attached. They're using R prime, R double prime, just to tell you the R groups could be different. But what we have then is we have an NH3 that's actually now attached, created a data bond here to the carbon, and the leaving group here was just in the process of leaving then. It's going to then go away, and that X group will now be given off as X minus. Okay. Now, why is it suddenly in NH2? It just turns out usually when I end up forming, I know an amine is the name for this family when I have an NH2 group. Usually what ends up happening here is I might have another ammonia present. And what would happen here is as the N tries to attack its way on the carbon here, one of these ends here actually grab one of the H's, and that ends up producing an NH4+. Okay? But nonetheless here we've added a nitrogen group on the compound. We managed to convert an alkyl halide over now to an amine. We now have an amine functionality here. This one here doesn't need any particular reacting conditions. Usually we might say heat just to get the reaction going, but no other special notes. Cyanide can also be another thing that attacks, another nucleophile. Again, it can attack via an Sn1 or Sn2, and it can yield a nitrile product. So a cyanide grouping here. Cyanide here, I would usually just write Cn minus like that. If you draw the Lewis picture here, it's actually Cn like this. Okay. Technically, both sides here do have a lone pair because we're going to end up forming a nitrile. We're going to end up having a Cn where the carbon attaches to the parent. I'm going to show you the carbon actually attacking. Again, the C has this electron-rich region here. It attacks the carbon on this side. The leaving group here is just in the process of leaving. We're going to have, again, our transition state, our carbon temporarily with the 3 attachments as we had before. And then we have our Cn group. We've now made the parent chain a little bit longer because I've now added another carbon grouping here. And we end up having a leaving group. Usually you just say X, and that bond there is just going to typically leave. Okay. Again, we're going to try throughout this chapter when we draw arrows, just the electron pushing. Both electrons are actually going this way. I'm going to prefer not to use like a data bond. Data bond, we also did that arrow there, but just note that as that bond there is sort of forcing its way on the carbon, the leaving group is also escaping. Then what we have is the leaving group is now gone. We have the umbrella flipped around, and now we have a nitrile product. So we've actually been able to convert to 2 new families now. Starting with a halogen alkane or alkyl halide, we've managed to create an amine functionality that has NH2, or a nitrile functionality. If you ever want to create those, this is one good way of doing it. Okay? So we've looked at nucleophilic substitution here. So far, we've just been doing Sn2. What I'm going to finish off in today's lesson here is looking at Sn1. We'll come back tomorrow and talk about when is Sn1 or when is Sn2. So let's talk about Sn1. What can we talk about this? The S refers to substitution. One thing is going to replace another thing. It's still going to be a nucleophile that comes in. The 1 actually doesn't refer to 1 step or 2 step. The 1 again refers to the rate law. The rate law is actually rate is K times just the alkyl halide, the Rx, which is actually a little bit strange. We'll see this as we go through here. This actually takes 2 steps. Okay, So if you want to just sort of memorize the opposites, Sn2 was 1 step, where Sn1 is 2 steps. I'm going to show you the 2 steps of this mechanism. So step number 1, the nucleophile hasn't even shown up yet. What ends up happening here is the C just spontaneously, this is just a proposed mechanism. What if this happened? What if the C spontaneously just gave up that X? This one here we're told as a slow step. Well, why would it, right? It's just the alkyl halide. But to some extent here, the carbon could do this. We're going to end up forming a C. We've tried this a couple times now. R prime and R double prime. I'm even going to use my wedges and dashes so you can see this a little bit better. The nucleophile isn't even present. We've ended up producing, this is a planar carbocation. Again, we're going to have a carbon that's positive, carbocation, and this one here is actually an intermediate. This is not a transition state. This one here can actually be collected. Sometimes it's going to be primary, sometimes it's going to be secondary. It just depends on the reaction. So basically, the leaving group has just up and left. Okay, really slow step. That's your rate determining step. In the rate determining step, you'll notice the reactant was only the alkyl halide. That's why it's only the alkyl halide. Nucleophile hasn't even shown up yet. Now, as step 2, in my Sn1 reaction, I'm going to take this carbocation intermediate. I have R, R prime, and R double prime here. Right. Because I am a completely flat structure here, my nucleophile, it could be hydroxyl, it could be amine, it could be cyanide, whatever. This hydroxyl can actually attack from either side. And depending on which side that it attaches to, you might end up getting the R isomer or the S isomer. Okay, so let's just use OH as an example of a nucleophile. OH is a really strong nucleophile. So what's going to happen here is the OH minus can attack from either side of the planar carbocation, giving rise to 2 possibilities. In this case here, if my OH minus, I guess I should write the O on the close side. If the O attacks the carbon and the umbrella flips this way, that's one possibility. What if the O attacks from the other side? Well, then I would have C with an OH. The umbrella would now flip. We have an R, and then we have dash to an R prime, and this one here to an R double prime. Okay, let's just say for argument's sake here, that's already in order of priority. If I have, let's say these are higher priority than the O here. If I have 1, 2, 3, and I look at it from the inside here, that's going to be clockwise. So that one may be our R isomer. If it flips the other way, again, using the same 1, 2, 3, usually hydroxyl is actually a higher priority group, but let's just say for argument's sake, if I look at it from this side here, I'm actually going to see that that's actually counterclockwise. Now we actually have the S isomer. Okay? This time there's no major product, there's no Markovnikov's rule or anything like that. Both are possibilities. And the kicker here is because we were planar before, the slow step only depends on the alkyl halide. The molecularity is just going to be 1. It could care less what the nucleophile is. And based on this, we would usually end up forming a 50-50 racemic mixture. So half R, half S. So therefore, it's optically inactive, or you can say optically not active. Okay, it will not rotate plane polarized light. Okay, so this is just another proposal mechanism. The reaction is still the same. The nucleophile has substituted itself on top of it. Let's look at some key differences here. The substitution actually occurs in 2 steps. The 1 does not refer to how many steps. The 1 refers to the molecularity. In the slow step, in the rate determining step, the reactants was only the alkyl halide. It's heterolytic fission as opposed to homolytic fission. Homolytic was an even splitting. This one here is actually an uneven or unequal splitting, where the carbon-halogen bond here just expels the leaving group, just ups and leaves. And then we end up forming a carbocation intermediate. That's the rate determining step. So therefore, as I wrote for you earlier, the rate is just going to be K times the alkyl halide. There is no nucleophile in this rate determining step. So being a 2-step mechanism here, the first step is just super slow. Why does the leaving group want to leave anyways? But once that reaction happens, then the other nucleophile, once it's present, it can add really, really quickly. So the overall rate is actually controlled by the rate determining one. This is the one with the highest activation barrier. So that's the slow step. So this is the biggest EA. So on a potential energy diagram, because it actually takes place in 2 steps, In this case here, the first step would have a big hill. The second step here may have a smaller hill here. The overall rate is dependent on this bigger step. Because it is a two-step mechanism, you'll notice my carbocation intermediate, carbocation not only is it planar, carbocation intermediate can be isolated. It is not in the process of breaking or forming bonds. You can actually, if you do your experiment right, you can actually collect this. Okay. This time the reaction only passes through a planar 3 coordinate. Right. It's not 5 things all together all at once. This one here is only 3 things all at once. The stability is going to depend on many things. Well, is it good for the leaving group to actually leave? Do I have the inductive effect from the alkyl groups? We'll talk about all that later on. In general, just experimentally, Sn1 reactions are faster than Sn2. So given an option, yes, while step 1 is going to be the slow step out of the mix, but if you compare an Sn1 or Sn2 step, we actually, Sn1 are typically faster. We're going to talk about whether it's Sn1, Sn2 a little bit more tomorrow. A couple of things just to take note of. We want to identify for a faster reaction. Right? Even for, okay, Sn1 is faster than Sn2, but how can I make the Sn1 even faster? I want to have a better leaving group. Okay. What do we mean by better? Well, why would this one here just up and leave if this one here, as that X minus here just sort of escapes? If I have things in the solvent that can stabilize it, if it's a very stable halogen group, that would help. So I can have a better leaving group. So that means it's more stable halide. That's one feature. We have to just sort of factor this in 2 different ways here. As we start taking a look at more stable group here, usually you'd say, well, the smaller that I am, the more stable that I am. So I want to make a note here when you make that comment here. Even though F is more electronegative, you should be able to explain to me why that's the case. Smaller radius, less shells. Even though F is more electronegative than I would expect that to be more stable. That one here should be the one that happens. Experimentally, I minus is actually more stable. That's more an experimental finding. And this also has to do with something we'll flesh out a little bit more tomorrow. When we start talking about alkyl halides and talking about the reactivity, because we have this carbon halide bond here, carbon, let's say C and X like this, and we can swap on whatever we want. We can swap on carbon with fluorine, carbon with chlorine, bromine, iodine here. One feature is going to be if this bond here is more polar, C and F are going to be really, really polar, that's going to really want to attract the nucleophile on, right? That's going to make it more reactive. But like we just said, experimentally, I minus is also more stable than F minus. I minus is easier at up and leaving than just F minus because the CF bond is actually a fairly strong bond. So in some sense, we might want to argue here, when the polarity increases, right, it should be more reactive, but that's not the only story. We also need to worry about when that leaving group leaves. We have F minus down to I minus. I minus is actually more stable as a leaving group. There's actually just many features that come into play to predict which one will be the fastest. Does it occur with the Sn1, Sn2? So more on this a little bit tomorrow. Okay. So have another look at Sn1, Sn2. Both of them involve a substitution with the nucleophile. Thanks, guys.